Okay, to all the audience of this podcast, thanks a lot for your interest for checking this out again. I'm Dawala. I'm a postdoctoral fellow at Technical University of Munich, and with me is Naman Jain, who is currently doing his doctoral research at the Max Planck Institute of Quantum Optics in Garching. So, in this series, we will be talking to women scientists and educationalists who have contributed to the community and they have a story to share with us. So, the message we are trying to emphasize is that to any of you who is listening to this podcast, and if you want to pursue science as your career, you can indeed do it. And the experiences of the people with whom we talk serve as a guideline to shape our thoughts and enable us to make informed decisions in crucial points of our life. That's the idea. And today we will be talking to Rama Govindarajan, who is an exponent in the field of theoretical fluid dynamics. She has been through various prestigious institutions such as IIT Delhi, Drexel University, Indian Institute of Science, and Caltech during various stages of her career. One of the notable achievements that stands out is that she is one of the very few women who have been honored with the Bhatnagar Award by the Indian government. Today, we plan to pick her brain, find out what she does in a greater detail, and listen to the stories that she has to share with us that have got her this far. So, thanks a lot, Rama, for your time, and we really welcome you to this Zeroing In platform.
Thanks for the opportunity.
Yes.
Yeah, so maybe we can begin with asking you perhaps the question that we really always try to start with is what interests you, or what sort of started you out, if you can remember, from your childhood into science, or was there something that you remember as a quintessential story?
So, from childhood, I think there's nothing special about me compared to all Indian children. If you're good in science and maths, or good is defined by whether you're getting decent marks in science and maths, then from a young age, you're encouraged to pursue that. And so I was in that thing where I would like to do science and maths. And also, as a kid and till I was grown up, I really, really loved maths. And I could have, seen myself in a career in maths. For that matter, if it was a different world, I could see myself in a career in history or some other cultural studies. So there's nothing, to put it very bluntly, like I don't have a calling. I've not born with a calling. It's just I worked for a long time in fluid mechanics and started loving it a lot. So that's basically the summary.
Like your childhood atmosphere was really like academic, and if you wanted to do you wanted to study, there was nothing that stopped you. So your atmosphere of childhood and family and schooling was all supportive, you mean?
Family, there was lots of support, but in school, I wouldn't say it was quite like that. They did support you to become good in maths and things like that, but they never once said that we should have a very brilliant career. In fact, my class teacher said on more than one occasion that we should all aim to pass the SSLC because otherwise we will not get a good husband. So that was my class teacher in high school more than once. So, yeah. But at home, it was a very, very different atmosphere because we had lots of women in the family who were already working. So it was quite normal for women to have careers in my family. My at least 7, 8 of my aunts had very fulfilling careers. People who are in their 80s now. And so those were my immediate aunts. A lot of them were working. My mother was always working. She was a single parent for the most part. we lived alone in Chennai with just me, my mother, and my sister, and she brought us up while working. And she is an amazing person. My grandmother's another amazing person who was born in 1907 or something like that. We don't even know her birthday. Um, she made up her mind. She brought up my mother and all as a single parent because my grandfather died young. And she made her daughters study. She never even once thought that her daughters would not have a career. And due to some very narrow margin, my mother missed being an IAS uh, officer. But my grandmother had paid the fees 3 times for her to take the IAS entrance exam. And that was in the 1950s when my mother took the entrance exam. So I come from a family where, women work. So that part was very normal and it was expected that I will work. Whether married or not was secondary, but I would work. And the second thing was that the one thing was that we didn't have that much money. Like, I was brought up by a single parent. We weren't like flush with funds. So I went to a government aided school, and I didn't expect to be, sent to the best college or something my mother couldn't afford. Those things were not on my calendar. So I wasn't told that, I could go abroad as an undergrad or any such thing. It was very clear that it would have to be in a government college with reasonable fees. And subject wise, they let me free. Like, they let me do what I like. They never, said, oh, you've got only this many marks, or it was never at home a big pressure to perform. So I could either perform or not as I chose. But my grandmother had bigger ambitions. Though she never pressurized me, she had bigger ambitions.
Okay, that's interesting to hear. Such, I mean, I well, by what you say, I see they were really far ahead of their times in their thoughts. That's pretty rare to see. So you were really good at math and physics. Then how did chemical engineering happen?
Oh, so like that again, it was just because that's what everybody does, right? Like you take the IIT exam. If you pass, that's brilliant. You immediately join IIT, whether you know about it or not. And you then, and in in your JEE, like depending on your entry rank, you get the best slot you can. As it happened, I got into IIT as one of the, tail end ranks, and I got into an MS in physics, the 5 year MS in physics. So from day one, it was my ambition to convert to engineering. That's because engineering is a, paying field or whatever. And so at the end of the second year in those days, and maybe in the first year in these days, in case there's a vacancy in the engineering departments, then you can apply, and based on your 2 year CGPA, a few people can get into engineering. And that's how I moved to chemical engineering. If there had been a vacancy in electrical engineering, I would have moved to electrical engineering. It's as simple as that. Like, no passion or something was driving me. And I don't think I was anything like remarkable in that.
But even shift in the in within, like when you are already in a college and a course, and then these shifts, I mean, these things are even like aspirational even now. But then again, most of the students end up sort of continuing with the career, and then now I think the trend is even very different. Most I mean, the focus mostly is in terms of jobs, which are also not core based. So was it a similar case at your time, or how did you look at this at the end of your engineering, perhaps?
Yeah, I mean, all through my engineering, basically, I wanted to take a job. And if I got a good job, I would work in it. That was my sense of it. But towards the fourth year, again, like herd instinct, everybody was writing GRE, so I wrote GRE, that kind of thing. So then I thought, okay, like what can be the harm of doing an MS abroad, like I'll get to see abroad. In my house, nobody in the house had even entered an airport, like let alone entered a plane or flown anywhere. So my immediate family, nobody'd seen the inside of an airport. So the first time I saw inside an airport, I flew straight to a completely unknown country, namely America, with no like real contacts there except my seniors from IIT who were scattered in various places of America. So I only had a few letters from my seniors to tell me what it was like. So yeah, I would have joined a job, um, and I didn't. I worked for a short time in Larsen and Toubro before I got the admission and went abroad. But yeah, maybe like since we're on this topic, it's kind of an old story which may or may not be of interest to people now because nothing like that will happen now. But maybe it's instructive. Like I got the job offer in Larsen and Toubro in a campus interview, and in IIT Delhi in those days they allowed us to get one job offer and one final interview. We could still attend one final interview, and so like I was shortlisted for attending the interview in Union Carbide. And so we had a group discussion in the morning and a personalized interview in the afternoon. And so in the group discussion, the Union Carbide team, like there were 5 or 6 of them, if I remember right, and they came in and they kept addressing all of us as gentlemen. And this was a bit strange because if there'd been 50 guys and me, I would have, understood that. But there were something like 6 or 7 guys and me. And so, like, it wasn't unevident that I was there, but they kept using the word gentleman about 100 times. And in the afternoon, they had the interviews, and each of my classmates, they interviewed for about an hour. And my turn wasn't coming, but when my friends came out, I was asking what did they ask, and I was noting down the questions, and I was getting ready with the answers. And then when I went in for my interview, they asked, oh, come in, sit down, like what do you like Carnatic music, Hindustani music? And I said yeah. And then they said, oh, that's so great. And I really thought this was the warm up for the interview, right? They're trying to put me at ease or something because it's a 1 hour interview. And then they said, oh, what instrument do you play? What do you sing? And then, thank you. Within 2 minutes, they said, thank you. And then I said, wait, I have a question. Can I ask it? And then they said, okay, you can ask it. And I said, from the morning, I was noting that you said gentlemen, gentlemen. And to each of my classmates, you gave a 1 hour interview where you asked real chemical engineering questions. You asked me only about my, virtuosity in music. Are you going to give me the job based on my answers? How are you satisfied with my interview? Is this a real interview or you're just rejecting me based on my gender? And they actually had the gall to say that they're rejecting me based on my gender. They actually said, in Union Carbide, there are dangerous chemicals and you'll be living alone in Bhopal and blah, blah, blah. And so we are not taking you. They could have told me that in the morning and, I could have had my another chance at a final interview. They wasted my chance at a final interview. And, but then I like to say that I owe my life to gender bias because if I joined Bhopal, there was the accident very soon afterwards. That was in 1984. So they were right about the
Thought when you said Bhopal, it reminded me that was this before the tragedy or after?
thing. And so the thing is, they were very right that there's dangerous chemicals, but they were not right about only which gender it's dangerous for.
But yeah, you said yeah, you pursued this chemical engineering, and I mean, just digging a little deeper, you went to masters. You decided to study, and you really didn't take the job route. I mean, while you actually started off conventionally, or thinking that okay, I'll study and because I want a job, as you said.
No, the masters was, to me, the masters was not like for increasing my knowledge of chemical engineering per se. That was an incidental. The main reason was I just wanted to see America. I wanted to see another world, and I thought like this is a very ideal way because it was 18 months. I'd planned it for 18 months and I said I'll come back and take a job. But this is my outing into the world. Like, I never expected that I'll ever go abroad again.
And
But
how was that experience like in general for you? I mean, given the 18 months of education there, how was that extremely different, or how did that sort of change your perspective towards academic career, or was that the time when you decided to?
so, I mean, it didn't particularly change anything. The one thing I noted is that I went to Drexel University, which is a very normal university. It's not some top tier university or something. But even there, I noticed that the teaching was really good. So that was one thing, that the teaching was really good. And I definitely became a better engineer as a result of going through some very very nicely taught courses and some very very nicely given homework. Not that I didn't have all that in IIT, but these were a little more advanced courses. So that was one thing. But apart from that, maybe it gave me more confidence, things like that. But I don't think I saw the research there and thought, wow, like I want to do this. In fact, my master's thesis advisor wanted me to stick on for a PhD, and I didn't. At that time, I was very sure that I want to work in industry. And it's only after many years of working in industry that I changed my mind and said I want to do research. So this is one message I'd like to give young people, not only from my experience but from the experience of many people I know. Like, some people are very lucky that they have a calling and from day one they know this is what they want to do. For other people like me, it's a blundering exercise. Like, you blunder from point A to point B till you find something you really like. And in my case, I found it later in life. Like, I started a PhD at 29, and then I realized this is what I want to do for the rest of my life. I think like it's okay to make those mistakes, it's okay to take those chances. And just because you're in a career or a job and you're scared of going backwards or temporarily moving into something more uncertain, you may not want to give up the aim of doing something you really like. You may still want to do something you really like, even if you're starting a bit late. And at least in my case, I'm very happy I did that. Otherwise, I would have been in a regular job, and probably I could have done well there. That's not the reason I'm saying this. And it could well be the reverse. Like, people may find late in life that they're not made for academia. So I'm not putting any caste hierarchy saying academia is better or industry is better. So even for me, it's not that at all. It's just that in India, in the milieu that was there in the 80s, I realized that probably academia is going to suit me better.
But when you were really sure that you want to be in industry, you went for masters, and although you were asked to join for a PhD, you said, "Oh no, I really want to do industry." Was this because you really liked this whole idea of industry, or is it well, because of some you really wanted to be stable financially, or uh,
So
I mean, what was
initially, it
your
was that
thought?
I wanted to be financially stable because I'd never seen that in my life. So the first thing I wanted was to be financially stable. So the initial thing that drove me was indeed that. But later on, I liked the idea that I could produce something, create something, be of use to somebody, like make money for my company or whatever, like come up with an invention or something like that. So in Larsen and Toubro, I had one senior called Sridhar. I still remember, like I mean, I used to really admire him because he'd come up with this idea of making a nice, you know, a device like a big a kind of burthen like this for making milk powder. So, like it used to dry milk and make it into milk powder. In those days, it was more for babies rather than the other one. But he came up with a very beautiful design for it, and it kind of personally struck a chord with me because I know that when my sister was a baby, she used to be given milk powder, milk made in a bottle, and that milk would never ever blend in with the water. So my family, my mother had to spend a lot of time beating the powder in so that some blob doesn't get stuck in the baby's throat. So she had to really work hard. Whereas later it became very simple, like you just pour warm water and it, yeah. And I felt that this guy is one of the people who brought about that. So I would have liked to do something like that which changed some product for the better. And in those days, like India was not an open economy, right? So many products were not up to par. So like when I went to America, I saw a clear difference in the products. Like in an average supermarket, an average thing would have much better, like it would have a sell by date, it would have a lid you can actually open without spilling half the contents. So like everything about it was great, like so I felt there's lots of room for improving products back here in India. So that was my goal. I actually like tried that. Was, I can say, trapped by marriage in Bangalore, and because of that I had to live in Bangalore, and then I couldn't get a very good industry job which suited me. And so I tried the industry that was available then, and it didn't work out. I tried, for example, Aeronautical Development Agency, and I had a permanent job there. I would have stayed on there if they had, allowed me to do like some of the innovations in the aircraft control system that I wanted to do. And I felt I was not being given room for that. So there were only
So
agencies like that where.
now I'm curious, how did you get interested in this aeronautics? Being a chemical engineer, is it more of an engineering mind?
Yeah, engineering mind and fluid mechanics.
Okay.
I already liked fluid mechanics a lot because I'd done a couple of courses in IIT and a couple of courses in my master's, and I'd also been TA for several fluid mech courses. And so, like, yeah, I mean, I was happy to be anywhere where I could do fluid mechanics, and I just saw this advertisement and applied for this job. And also, I'd done control theory for my master's thesis. So that kind of suited very well. In those days in Bangalore, I had two choices, like aeronautics or software. And software was in its baby stage, like fledgling stage. So I chose aeronautics.
So how did it what made you really sure that academia is what you want to do? How did that transition begin?
At this time, when I was kind of disappointed in what effect I could have, in fact, like I wasn't even given work to do, like I mean, and at that time I decided, no, like I have to do something and do something creative, and um, if not in industry, let me try academia. And then I got this lucky break because I moved to NAL, and in NAL, like the ideal was that I could do my PhD with Narasimha. And so you can say it wasn't a complete jump from industry to academia. It was a jump from industry to NAL, which is a kind of industry and kind of academic environment,
It's intermediate.
intermediate thing. And and I got a permanent position in NAL, which I could have stayed in forever. And then I got this PhD thing. When I completed my PhD, they allowed me to go to my postdoc in Caltech. with the 3-year bond. So when I completed the bond, at that time JNC came up. So it was a very good opportunity for me to apply and move across. So yeah, it was all blundering and more blundering. Nothing to be impressed by.
Yeah, just to keep the audience on in the same page, when Rama mentioned Narasimha, she's one of the privileged students of Professor Roddam Narasimha, who's, I think, the icon of Indian aerospace in general. Can you tell us? Uh, Unfortunately, we can't talk to him, but can you tell us how did you meet him, and I mean your first memories of working with him? Or can you tell us about that? How did you start your PhD with him? Like, was he?
I basically approached him and, um, asked to like work in NAL with him. And he gave me one test problem to see if I'm worthy of it or something. So it was a problem that one of his PhD students was working on, and one of those little sub problems that this other student was doing, he gave it to me. And then, like, based on, and he said, come back in a week with some calculations. And at the end of that week, when I came back with calculations, he said, okay, like, he can work out a temporary position for me in NAL and then see whether I work my way up to a permanent position. So that's how I started working with him. It was always a pleasure working with him, but I could never find him. He, like you said, he was this icon of Indian aerospace, and not just aerospace but also of atmospheric science, a whole bunch of uh, disciplines. And he was always traveling, he was always meeting important people, and he was director of NAL. That was no joke in itself. So, like, yeah, I didn't get much opportunity to work directly all the time with him, but he had very crucial inputs to my PhD, and it was a pleasure working with him. And I was always in touch with him till the end of his days, and he was always a pleasure to talk to and work with. And he had a razor sharp intellect. So he could immediately catch hold of things. He could immediately suggest non trivial paths to take. He could understand what I was saying within a minute or two.
At the time, I mean, how did you stumble upon your PhD problem, and how did you decide to, or what paths did you take at that point? Uh,
Okay, so every day I would sit in the NAL library for 5 to 6 hours and read all the latest journals. Latest means they would have come by ship, aram se, so like they'll be a few months old. So I would read all of them and I would try to find gaps in knowledge. And especially like Journal of Fluid Mechanics, journals like that, I used to read a lot and see what's not been solved. And that's when I worked out that stability, flow stability. There were so many aspects of it that were not understood. I also noted that there were several papers on boundary layer stability, but they were all contradicting each other happily and giving contradictory answers happily. So that gave me like a question to um, latch on to. And when I spoke about this problem to Narsima, I just mentioned the field I'd like to work in. He said probably Professor P.K. Sen in IIT Delhi can help me with some coding stuff I was getting stuck in. So I went to Delhi and got help in the coding stuff.
Can you tell us in a simple way, if possible, what was your problem? What question did you ask? In if it's possible.
The thing was that there is an aircraft wing on which there is a thing called a boundary layer, a thin layer within which the velocity changes by a huge amount. So the air outside is not moving at all, and the wing is moving at a high speed. So the air from here to here is changing in speed from zero to a big number. So that thin layer is in laminar flow near the leading edge of the wing, and then it goes to turbulence and then stays turbulent for the rest of the wing. If you can delay the laminar turbulent transition, not delay, but push it back by a percentage or two on the wing surface, you can gain like billions and billions of dollars in fuel, because you'll spend that much less in fuel because laminar drag is less than turbulent drag. So the problem in those days was, can we push it a bit to the back? And then I started looking at the theory of boundary layer stability, and I found this thing that everybody had a different answer. In fact, they were not even working on an aircraft wing, they were working on a flat plate. Like, for example, you take this book, okay? So if this book is moving at speed v, and it has no wing shape or anything, then when does that laminar boundary layer go unstable? And going unstable is the first step in the route to turbulence. It doesn't become turbulent as soon as it's unstable. In fact, there's a long transition zone where it's neither laminar nor turbulent. But yeah, that first instability, very first instability, people were getting wrong. Like, they had 4 different answers in the literature, in top journals. Like, they didn't seem to worry that they were contradicting each other.
So was it the problem that you're mentioning in terms of contradiction? Was it purely a theoretical contradiction? Why was it so hard? Because wa- wasn't it possible to experimentally verify which one was right, or am I simplifying things?
Experimentally, this problem is very hard. Like, even today, it's not too many people who do. The reason is that, you have to put pure noise of a particular frequency, you have to have a particular shape, and you need very good velocimetry, like ability to measure velocities. And it's not very easy. The transition point is easy, but instabilities are not at all easy to decipher experimentally. Although, like, even in the 1940s, somebody done this flat plate experiment. In the Second World War, somebody had actually got an answer for that. But mathematically, this problem is very, very complicated, because it falls in a class of problems called singular perturbation problems. That means that the highest derivative is multiplied by a very small number. So if you have something like x double dot plus x dot plus something is 0, just an ordinary differential equation. If you multiply the x double dot by epsilon, then, like, your tendency might be to throw away that term, because it could be multiplied by 10 to the power minus 10. But if you throw that term away, you can't satisfy 2 boundary conditions. So this is a class of singular perturbation problems. And the point is, this boundary layer keeps growing as you go downstream. And that brings in this very slow growth, brings in a big singular effect. It can bring a big strange effect, which is not singular in the traditional sense of it being multiplied by the highest derivative, but it brings in singularities in a different way. So mathematically, it's very easy to go wrong. It's basically the spatial variation of the boundary layer. So I did the flat plate, and then I did, like, wedges and wing shapes and things like that.
So this was what you asked or solved during your PhD, is it?
Yeah, in fact, like, the code that I developed, Boeing purchased that code.
Wow.
For a small amount of money, but I was invited to Seattle for 3 weeks to put that code on their machine and explain to everybody how to run it.
It must be, a huge, sense of accomplishment to have them get, have them take your code and.
Yeah, I actually don't know how much they used it, because I moved on from aerospace soon thereafter, but they actually bought it.
Okay. So maybe when we sit in the aircraft, there is something of your code going on there.
I don't know. It's
But
most likely not, but
while you were working on these theoretically motivated problems, did that bug of actually using these to apply to something that's practical and useful to the society, did that still remain? and how did you actually like come across it? Because of course, I mean, fluid mechanics or fluid dynamics has been a field which has been extremely interesting for now probably a century more, and it has always been theoretically interesting, and applications have been massive. So how did you choose your problems there and then later on also?
Okay, so the point is as follows. Like I explained to you already my PhD work, and the fact that it was a singular perturbation was brought to my notice by Narasimha. Like I would have never worked that out if he didn't immediately say, "Oh, this is why you're seeing all these big jumps and whatever." Yeah, it's all natural, that kind of thing, and that was a very very important contribution of his, even though it took him like 2 minutes to say it. But so then, like when I started hitting out as a faculty member, I've always been interested in chem-eng type problems. So I went back to problems which are motivated in chemical engineering, like polymeric flows, things like that, various such things, and especially flows where some property or other varies in space. So when I started looking at those problems, I started using. I started seeing singular perturbations everywhere, briefly, and that was not very standard in chem and fluid mechanics. Aerofluid mechanics is a bit different in the way you look at things. So I could merge these two things, like bring mathematical aspects which were well known to some small subset of aerospace engineers into chemical engineering problems. So I started looking at problems like that. I could find some new instabilities. And then that, like working with all those things, naturally took me to multi-phase flows, and that took me to things with some geophysical applications like earth and climate type applications now. So that also started because some of Narasimha's other students were working on clouds already, and by attending their talks and things, I got some notion about what this was about. So I slowly meandered. Of course you have to meander, like in science, that is not a part I'm saying is bad. Like you can't be doing your PhD problem for more than 5 years after your PhD. You have to redefine something and like learn new things and move on.
So back then, you did your PhD with Nasimha, and I mean, I think that was the best person with whom you could possibly work in India.
Yeah,
And then you,
definitely.
yeah, and then you answered some of the really important questions. You have accomplished. You were an accomplished PhD student in terms of the scientific knowledge that you had developed yourself. And then you go to Caltech, which is also an amazing place to be. Uh, can you tell us about the difference? Was it massive difference in terms of problems that they were asking to what Indians were asking? How was that scientifically?
So I went to the group of Anthony Leonard in Caltech, and they were asking a lot of, I mean, they were aiming higher, I would say, on an average than Indians were at that time. So that was really, really a great experience because there were these other students and postdocs in the group, and we had a very, and that was the part I told you I missed in my PhD. So it was very nice to be in a group where everybody is looking at similar problems. You're talking across people, you're giving suggestions, you're getting suggestions. And so, like, it was intellectually a much more relatable atmosphere because they were doing similar things. Everybody was doing similar things. Like in NAL, also, some people were doing very nice things, but they were a bit removed from what I was. So, like, this was very intellectually rewarding. And also for confidence, it was very rewarding because in those days we didn't have email, we didn't have any notion of what others are publishing. I mean, unless you got hold of somebody's CV, you wouldn't know like whether they're doing better or worse. So, like, you always thought that, oh, by definition, everybody in Caltech is better than everybody in India. So, you
So yeah, because you mentioned this, that those were the days when until you pick a CV, you don't know what others are working on and so on. Now it's you have seen this massive phase shift in attitude or in general the way science works. Now it's like the moment you hear a name, you can type in a name in Google, and you know the whole biography of the person. You also get a rating for that person in the name or in the form of H index and all kinds of numbers. Can you tell us what do you think of those days versus these days? Are you would you given a choice would you go back to those days where you peacefully sat down and did your research, not caring about what others did, versus today?
I would say that the present day it's way, way, way better, and access to information is very important. You need access to information, and it's more competitive. You have to work harder. All that is true, but all that is needed, and I think it's going in a very good way. So, on the whole, I'm not even on the whole, I'm very, very sure that this is the way to go. Hmm. The only thing is that there were some very nice things in the old days which we shouldn't lose track of, which is like, suppose you come across a problem which is very deep and very hard, and it's not going to give you immediate moolah, in terms of papers or whatever it is. You should have the wisdom to go after that as well. Of course, you have to do things to keep your profile up to date or whatever, but it's important to ask those hard questions. You should not like get trapped in a shallow place where you can write a lot of papers with the one little thing or something like that. I'm not saying people are like that, but I'm saying there is something to learn from the old. But the new is much, much better. I find the young people of today are so much better than I was at that age. They're so much more knowledgeable, they're so much more deep. So I don't have any, that kind of nostalgia to go back.
But how about you're a theorist? There are two questions which I am always curious about. One is that uh, uh, you use computational facility extensively, and those were the days when the computational facility was so limited, as opposed to now where the computational facility, of course, there's always a limit that you keep pushing. It's way better than what it was earlier. Has this contributed to how has it contributed to answering the scientific questions compared to back then and now? Uh, uh,
For me, I've always been dreadfully and woefully short of computing. The computing I need, and that's not like much changed now. I mean, now also I need a computer that should be 1,000 times more powerful than I have. So, like, I can't do a cloud simulation. So, that
yeah.
didn't change too much.
Okay.
But, and the kind of code I write, yeah, like, I mean, coding has improved a bit. But yeah, I don't see any deep change in, it's true that some of the questions I asked today, I couldn't have asked them. But that's been a natural progression.
Okay. Okay. So you're saying that the computational progression has not made a big impact on not.
I'm not saying it's not made a big impact. I'm saying that it's always been inadequate. But it was inadequate small and inadequate big, whatever. So that's the only difference. And yeah, in terms of computation, I think we did hard computations then as well. They may not be, very big in terms of computer time or RAM or something like that. But we asked hard questions and made the computer answer them. We devised new techniques to answer them. So I don't think our coding was super unsophisticated. It wasn't. That wasn't at all different. Now you have access to more packaged code, that's all.
Okay. I'm curious about what you do now as a group. I mean, you're a pioneer scientist leading India in this field now. What are like what are the kind of questions you ask now?
Okay, so how much time do I have to tell you that in? 10 minutes?
Yeah.
Okay. So, the big problem I look at, one of the big things I look at is when you have particles or droplets in a flow. So, for example, in a cloud, you have little water droplets, teeny tiny water droplets. In a volcanic ash, you have, you know, a lot of ash itself. And in river sediments, you have these mud particles which are going into the ocean or which are being carried by the river. So, almost every natural flow you could think of andhi. I don't know whether you know what andhi is. Dust storms, you have like particles in flow, and one of the things we ask is like how do these particles affect the flow, and how does flow affect these particles, and what happens as a result of this. So one example that I would be interested in is in the ocean you have these little critters called plankton, and the smallest and the most primitive ones are called phytoplankton, which drink, basically they're living matter, so they contain carbon, so they actually help deplete carbon in the atmosphere, so they can help clean up our environment. And then their fecal matter and their dead bodies sink to the bottom of the ocean, and that takes carbon to a place where it won't be released too soon. So this kind of impact of particulate matter, and so like living matter also is counted in this. So we start from a very simple, the simplest equation, which is already very messy, called the Maxi-Riley equation, which describes the motion of a small sphere in flow. And because the sphere is so very small, the flow is basically the leader, like it tells, I mean, it basically takes the sphere where it wants to. So the sphere is almost at the same velocity as the surroundings, and the difference in velocity is very small, the size is very small, which means the Reynolds number is very small. And the Reynolds number is a ratio of inertia to viscous forces. So viscous forces dominate on this body. And so, like the Maxi-Rayleigh equation describes what is the right equation. It's actually what is called the unsteady Stokes equation for a sphere. Written for a sphere is called the Maxi-Rayleigh. So it's a subset of the Navier-Stokes equations. But because it's written for a sphere, it's specific in that there is one body going in the flow. Now, that equation looks like it looks, it's been used for decades, so it looks easy, but it isn't. There is one term in that equation which is mathematically very, mathematically it's easy to write down, but computationally it's very, very heavy. So it involves, like, it's called the Bassett-Boussinesq history force. So, like this particle, wherever it has been in the past, everywhere it's been in the past, its acceleration in that place x where it used to be in the past, in x past, minus the fluid's acceleration at x past, that difference in acceleration all through its history gives a resultant force which appears as an integral over all time on that history with a complicated thing in the denominator. So, if I want to just take one little sand particle in an ocean, in a river, and ask like how it reaches the ocean, in order to do that calculation, I need its entire past. Okay, and at every time step t, I have to perform the integral from 0 to t. And at time step 2t, I have to perform that integral from 0 to 2t. So each time I have to remember that many pasts. So my memory requirements go up with time. And this is all for one sphere to get it exact. Now, in a cloud itself, in one cc of a cloud, this much of a cloud, there are like 500 water droplets. What they do in the turbulent flow is the question. And we know that clouds extend to like thousands of kilometers. So there's absolutely no way to solve this thing accurately in any modern day computer. So when I said computers are inadequate, you won't find a single fluid mechanician anywhere in the world who says, yeah, it's adequate. Because it is inadequate. Nobody can solve all these things. So we do the best we can. So like the my colleague Vishal Vasan in ICTS, he came up with a brilliant method to solve this with limited memory requirements. So that is one aspect which a PhD student is looking at. Like, how do we use this new technique to understand about different things that happen in the flow? And then there's another student who's looking at Stokes' flow again. But what if there are multiple particles who can affect each other? So, right now, we're living in this world where this particle is living alone in a flow. But that's not the case. Particles can affect the flow, and the flow can affect the other particle and their behavior. They can cluster, they can do very interesting things, or they can repel. They can be effective repulsion, though they're not chemistry wise repelling.
There
So
is some
interesting
interaction.
hydrodynamic, huh?
There is an interaction between them,
Yeah,
basically.
the hydrodynamic forces can create effective clumping and stuff like that. So, and this becomes even more interesting when you have, instead of spheres, you have spheroids, like ellipsoids. So those are questions we're asking, and we do like lots of pen and paper work in this as well as computations. And one more student is asking, like I told you about this boundary layer stability and those how the laminar flow goes to turbulent, right? So what if the laminar flow had particles in it? So what if I'm looking at flow through a pipe which is particulate, which is very frequent in chemical industry and all. So then how does this, the effective interactions between particle and particle, how do they change the laminar turbulent transition? So these are like some particle questions. There's one student who's looking at something very out of the box, which is on helicity in turbulence. So helicity is a very beautiful property. It is so there is this velocity vector u, and there is a curl of u. So if u is varying from one place to another, you have a curl which is in the, so let's say there's a shear here, then you have a curl which is pointing in that direction. They need not always point orthogonal. They can be a u dot omega, a velocity dot vorticity, curl of u being the vorticity. And this property is the helicity when integrated over all space. And in turbulence, in inviscid turbulence, that means when there's no viscosity, this is a conserved quantity. So then, like, what does viscosity bring to it? How does the flow become helical? How does helicity get injected into the flow? How does it get removed from the flow? There's beautiful mathematics. I should say that all my group are amazing people, and I learn a lot from them, and it's great fun working with all of them. So, this basically gives you an idea of what I do. So, it has like implications for clouds, implications for ocean. There was one student who worked on the ocean who's now graduated, but I don't directly attack climate problems, as you can see. But our methods may become useful for those problems because we find ways of doing it better, or we understand something simple in it which can be a feeder into the physics when you're doing a big simulation, when you cannot resolve these scales. I hope that gives you an idea.
Yeah, it does. Yeah, I think it's leading to too many questions, and I think I mean, all questions cannot be answered right away. One has to really know what questions to ask as well, because most of them would have been already answered. But something very general to the audience, or even to me as a naive person with regard to your subject, is yeah, you take inspiration from clouds, volcano, ocean, and so on. And then you write down mathematical equations to understand them. Now, this is like really two ends of the spectrum where there is something real happening, whereas in mathematics, you are it's abstract and you're modeling them out. Uh, where do you draw the line, or how what is the approach of a theoretician when you are trying to model a very real system, writing down it in a very simple way? It's
I wouldn't use the word model here. I wouldn't use the word model and I wouldn't use the word inspiration. It's not that the cloud inspires me. I look at what's going on in a cloud. I try to pull out one aspect of it that's not understood physically,
Hmm.
and I try to solve for it as correctly as I can. So it's not a toy problem that was inspired by the cloud.
Okay.
That's very important to know. It has actual relevance. Okay. Secondly, so it's like a subset problem. The important thing is to know it's a very complicated problem overall. So it's important to know what I can peel off and what I can solve for. In the thing I can solve for, after I peel off things which may or may not be justified, but I should know whether it's justified or not, or how poorly justified it is, so that later in life I can go back and release those terrible assumptions one by one. But in the subset, we actually try to write a real force balance. We try to write real equations, so the mathematics is not pulled out of a hat. It's mechanics equations that come out. And if you're lucky, you get a brand new equation which nobody solved before or nobody got before. So you feel very happy when you get a new equation, but we're actually writing the force balance equation. So Navier-Stokes is basically Newton's laws for a fluid, and in that we have these particles moving around who force each other. So does that give you an idea?
Yeah. If okay, so now I mean now the thing that I'm a little confused is while you write down real equations and it's not like abstract mathematics being really forced upon something. What is it that's complex about the problems that you do? Is it the sheer magnitude of the number of particles, as you said before, that it's massive? Is that the problem, or what is it that's the most complicated thing about getting a real, completely real understanding of a cloud, or I don't know, something that you're looking at in a massive scale?
So the big problem in our field is so you can say that if I have this infinite computer, I can solve for everything. The real problem is that there is different physics going on at each scale. There's physics going on at the micron scale, where tiny little particles are running around. And there is physics going on at the 1,000 kilometer scale, where clouds are aggregating to make a formation, or the efflux from a volcano is going to other continents, pollution is spreading from one continent to another. So there are these very big range of scales, and earth's rotation becomes important at some scale. It can be neglected at some other scale. And being a non-linear problem, being an unbelievably non-linear problem, every scale can force every other scale. So because of that, like if you work in one scale alone, you're in trouble. So you have to do something for other scales. So I think the whole community is looking at things at different scales and trying to come up with ways that they can talk to each other. So people who do climate modeling may be missing out everything in the small scale, and they may be getting some of it wrong because and that's why we can't predict Indian monsoon well, because we don't know the cloud things well. And so our aim is to start at the first principles place, where we say, okay, like this is turbulence and this is turbulence in a little box. Let me get that straight. And then we'll see how it's forcing the bigger scales and so on.
Yeah, I mean, that gives a fair idea of what it's all about in a very general way. As a naive person, if I study aerospace or aerodynamics, what are the things? Is it only academia that has an option for me in future, or what are the places where these things are relevant? The studying this subject.
Okay, so I have not kept in touch with the latest in aerodynamics, so I can't really answer that question with authority. But one of the things that is likely to come back into existence is these aerospace planes. And space travel is going to become much more common. There's no going back on that. And even aerospace planes are a thought which, and supersonic flight may come back. I mean, once in a while, I mean, it's very sad that the supersonic aircraft that were there were grounded, but that may come back. And, there's ample opportunity in speeding up flight. I would say that we should actually go the other way. We should actually try to reduce the number of flights we have and become more green about it. And so there's possibly lots and lots of also avenues for fuel reduction, like if you can make the aircraft themselves greener. That I don't think will ever be a closed subject. And that is about aerospace. But I would like to say also about climate science, like, a lot of physics students don't look at climate as one of the things they want to study. Like when they go in for research, they think of, I don't know, like, I mean,
Yeah.
string theory, condensed matter, like some traditional areas. But climate is going to be big. Climate is going to be really big, and people should do it. And in India, we have so many problems to do with climate, so we badly need young good people, not only in physics but also engineering and all other disciplines, to come into climate science. And there the opportunities will grow. The questions are big, the questions are beautiful, and they are going to be helpful to humanity. So you don't have to go out of your way to be helpful. And yeah, from every point of view, they're very basic questions, things that are not understood at a very fundamental level. I mean, everywhere you turn, there's a PhD problem. It's that big, and like young people should recognize this and come to it. And not only in science, but there's borders between science and social science, science and humanities, which become very important in climate. For example, like, what if some parts of India get so hot that people start migrating out of there? So even to optimize livelihoods is a research problem.
Yeah.
It's a research problem of enormous proportions. So there'll be problems which we haven't designed or thought of till now. And young people should already think of them, should already work on them. We should not wait till some humanitarian disaster happens. We should already circumvent that humanitarian disaster.
So, are there programs that are already looking into these broader or bigger picture problems in India? Or
So there are, but they're smaller in number and size, everything. So we really need to expand in that. So there's already excellent people in climate science looking at particular aspects. And they're people with a deeper understanding of it, certainly than I have. But we need far more work to go on.
the magnitude of people required, as you said, is really way order of magnitude higher than the number of people who are already there.
So I think it's an opportunity for the young.
So this is really interesting because it's most commonly, at least even in this forum, and what you see in general are problems that are driven either by the word quantum or technology driven and so on, but we are sort of missing on some of the basic aspects of science that are directly related to humanitarian uh, aspects.
Yeah, yeah.
Yeah. Naman, if you have more questions, else I would ask Rama to just let us know something that you would want to give as a message to all the audience here.
Yeah, I think that I would also ask the same thing because yeah, I mean we're closing soon, so yeah. If we missed anything that you would like to talk about, or in general, if you had any ideas that we missed talking about, please.
No, this is the two messages I want to give. Like, don't be scared to pursue your dreams. Don't be scared to realize that what you thought was your dream is not your dream. Don't be scared to change. And like, be aware that there's lots and lots of big problems. So, even if you want to do humanities or some other thing, like, do it. There's lots of ways in which you can be very, very useful to society. So being useful to society and being having a fulfilling career doesn't stay with science alone. There's no special thing about science. So don't feel shy and don't worry about which has a bigger closing rank like I did. Choose the one you like.
That's actually a very important message to youngsters, because most of them complain, or I have heard very often in present times people saying, I need time to figure out what I do, and people end up spending a couple of years or even more simply staying idle, or they are really afraid of the fact that they don't know what to do. I mean, it can take time and still you can, I mean, when you realize it, you can really make big impact, as you're a great example for that.